5. So in this video, I'm going to talk about finite differences. So finite differences is a method to solve boundary value problems and also partial differential equations. We already briefly covered using polynomial collocation. Finite differences is just another way of solving boundary value problems. There's actually lots of different methods. And depending on different applications, certain methods have strengths, others have weaknesses. But in general, finite differences is a pretty simple and powerful method for solving both boundary value problems and partial differential equations. And the key idea is that we're going to take a function which nominally requires an infinite amount of information to represent as a finite number of points. And we've already actually played with this idea in the past when we plot functions. So just to illustrate this point, so imagine we have a function, and I'm just going to call it, I don't want caps lock. So we have a function, and let me just make it general, lambda x, and maybe we'll just do sine of x. And let me run that. And then maybe we want to represent that as a fixed number of points. So maybe we'll do 20 points, and then we'll do our x is np lin space. Just put a space here. And we'll pick a nice domain from maybe, let's do from -4 to 4, and then we're going to do n points, and then we can just plot this up. So we do plt plot x, f of x, and then we're going to do line width, we'll do circles, line width of 3, and then color is equal to blue, and then we'll do plt show. And so we have a representation of the function where each point is represented as a dot. And the distance between these points on the x-axis is all equal. That's what lin space is. It gives us equally distant spaced points. And we're representing this function as a finite number of points, and then we're just drawing a line segment to visualize it between the points. Obviously, if we pick more points, so if we did 200 points, we're going to actually get a closer representation of function. And this is kind of what we do already when we plot functions up. But let's come back to n equals 20 for our picture. Now, the question is if we're going to solve a boundary value problem, basically we have to be able to take derivatives of functions. And what we can do here is actually take advantage of the definition of a derivative. So here I'm just going to put an equation in using Markdown and LaTeX. So if I think about df dx, that's going to be approximately equal to basically f of x plus delta, where delta is a small number, minus f of x, and then I'm going to just divide it by delta. And Markdown, and so I have an approximation for a derivative. Now, as delta approaches 0, if we take the limit, this will exactly give us the derivative, but we can get an approximation if we pick delta equals small. Now, in this case, delta is going to be the distance between our points. So in our case, delta is going to be simply x of 1 minus x of 0. So it's the distance, and we can print up delta. And in this case, we're going to find it's equal to 0.421. We could also just use the formula based on n, that delta is equal to the width of our domain, which is 4 minus 4, so 8, divided by n minus 1. So in general, the formula is going to be kind of the width of our domain divided by the number of points minus 1. And we can also print up our delta value. All right, so we can use either function to determine our delta value. Now, in our case, as I mentioned, all of our x's are evenly spaced, and the distance between them is delta. So now imagine we want to take the derivative of this function. All right, so we're going to come back down here. All right, so I'm going to pick n is equal to, let me just copy this code up here because I want to keep it and I want to be able to change things. So we're going to try to take the derivative of sine. Now, basically, if I come back to this function, right? So if I think about an x, so let's just take this x value, and I want the derivative of the function at this value. Basically, this formula is saying we want to take the value at x plus delta, so this y value, subtract this y value, and then divide it by the distance between those 2 points. And the way we set it up is that basically this would be x, right? And then x plus delta is just the next value of x in the array, right? So that'll make our life a lot easier for calculations. And again, we're looking to the right to determine the slope, and we're using the center point. So again, this is the derivative at this point. We look to the right, subtract this point, and then divide it by delta. Now, one of the things when we use this formula is that since we're always looking to the right to determine the derivative, we can determine it for this point, this point, this point, all the way up to this point. But our last point, we're not going to be able to determine the derivative. In our case, in boundary value problems, that's not going to be too much of an issue because typically these kind of n values are going to be specified by like the boundary condition, but we can also use another finite difference formula, and that's known as the backwards difference formula. And so that's frac dx. And let me just copy all this because it's just a minor perturbation. And what we're going to do here is rather than looking forward, we are just going to look backwards or look to the left. All right. And so this is actually also an equivalent representation of a derivative. So this last point, we can determine its derivative by just looking backwards, right? So we take this value, then subtract that value from it, and then just take the distance between the two of it. What's nice is that when we're going to increment it, so if this is x of I, then x plus delta is just going to be simply x of I plus 1. And then if this is x of I, this is just going to be x of I minus 1, because that's how we've set it up by choosing the difference between these points as delta. So if I want to do the derivative of sine, right, and I'm going to just do list comprehension, right, so I'm going to just type in this formula. So I'm going to type f of x of I plus 1, so that's that's going to be our x plus delta up here. Then I'm going to subtract the f of x of I, right, and then I'm going to take this quantity right here, and let me put a parenthesis over it. And then I'm just going to divide it by delta. And then I'm going to do for I in range. And I'm only going to go to n minus 1. And again, I'm going to n minus 1 because I don't want this last point because I can't look to the right of it. I'll get an error if I try to take all n points. And then let me just make sure this works. And everything's golden. And so then I can just plot it up. So I can do PLT plot. We're going to take our x values, but we're going to grab every x value except the last one. So we're going to do colon minus 1. So that's everything up to, but not including the last point. And then we can just do df. And then we can do, we'll just do our thing here, line width 3. And then let's equal color equal to blue. And then we can do PLT show. And we're going to have basically a finite differences approximation of the derivative. If I wanted to look at the true derivative, right, so I could do PLT plot x. The derivative sine is cosine, and then let me just do the same. Dash 0, line width is equal to 3, and then we can do color is equal to red. And you see that they're not exactly matched, right? So the true derivative is a little bit shifted to the right. The reason why it's shifted to the right is because basically when we calculate the derivative up here, we're looking to the right to calculate the derivative. But we can kind of fix this by just picking more points. If I'm going to pick 200 points, what am I doing wrong here? It should be df. That's n. Oh, I forgot to correct the delta. So I got to do delta is x of 1 minus x of 0. And now you see that they're exactly overlaid. So I had to redefine the delta here because the delta up here was defined only for n equals 20. I didn't run that part of the code to update it. Last thing is if I want to get that last point, so let me come back to 20. You see that there's this 1 point missing over here for the derivative. Well, I could just use the backwards formula, and here I'm just going to do an append command. So I'm just going to append. And so we're just going to grab x, the last point, minus f of the second to last point. So this is our backwards difference formula. So here we're using this formula here. So we're taking the last point of x and then the next last point of x, which is minus 2. We take this quantity here, and I think I got all the parentheses, and then I'm just going to do delta. See if that works. And I'm probably missing, let's see, what am I doing here? Append. I got that. Who are you friends with? I forgot to do this parenthesis right here. And I run it, and I still don't have it right. And now I can take the full value of x. And you're going to see, again, we're going to have a derivative. Now we got the last point in it. It's a little bit off, right? But as we kind of fill out points, so if we did 40 points, we run it again, and now we start seeing better and better approximations to everything we're looking at. And then finally, if we did x equals like 100, right, we're going to have almost perfect overlap with the two functions. And so in general, as you add more and more n or more points, you're going to get better and better approximations. If we did 1,000 points, obviously it's going to be pretty much the exact derivative. The nice thing about this is, obviously sine, we know how to analytically take the derivative, but this function would work for basically any derivative. So if I did sine squared, I'm going to get the derivative of sine squared. I don't even know what that is analytically. It's going to be like sine times cosine or something like that. 2 times sine times cosine. But now we get our derivative, our finite differences derivative. Now, just as we did first derivatives, we can also do second derivatives. So the formula for second derivatives, and let me just go down to markdown. And here what we're going to do is frac d squared f dx squared. That's going to be approximately equal to, and now our formula is going to actually have, looking at f of x plus delta, and then minus 2 times f of x plus f of x minus delta. And then we're going to take all this and we're going to divide it by delta squared. And typos, and let's finish this off. And run it, and this is going to be our formula for our second derivative, right? So we're going to look to the left, look to the right, we're going to look to the left, subtract 2 times the current point, and divide by delta squared. So again, if I start off with my initial function, right? So I have my initial function. Here, when we take the second derivative at, say, this point, we're going to have to look both to the right and to the left of that point to determine the second derivative, right? Because we're thinking about the curvature. And to get the curvature, we actually need to look at both the left and the right to get a sense of that. The other thing is, just like as before, the endpoints we don't have a formula for, right? Because at this point, to determine the second derivative, we can't look to the left of it because that's not defined. We can only look to the right. And likewise here, we can't look to the right. We can only look to the left. But it turns out, as you'll see when we start solving boundary value problems, that we don't actually need these endpoint values because we're going to determine those using kind of from our boundary conditions. So let's come back. We have our function sine, right? And let me just delete this part out. And we want to do our second derivative. Whoop, come back here. And our second derivative, we're just going to do d2f. And we're just going to do list comprehension again. So we're going to do f of x plus delta. So that's going to be I plus 1. And then we're going to subtract out 2 times f of x of I. That's the x value. And whoop, having some problems. And then we're going to add f of x of I minus 1. And then I'm going to put parentheses around everything. And then I'm going to divide it by delta squared. In general, I typically, rather when I do squared, I just divide it by delta delta. But I could do delta delta. And then for I in range, and here we're going to go from 1 to n minus 1, right? And then let me close off the list comprehension. Let me shrink this down so you can see everything, right? And so we have our formula. So this is x plus delta. Here's the f of x. Here's the x minus delta. Here's the delta squared. And then because we can't get the last 2 points here, we're only going to do the interior. So this is point 1, and we're going up to, but not including the last point, which is the n minus 1. And so if I want to plot this up, PLT plot, I'm going to do x. I'm going to go 1 to minus 1. I can do d2f. And then I'm going to do my values. So line width is equal to 3. Color is equal to blue. And we know also that the derivative, right, is just going to be minus mp sine of x, right? So if I take the second derivative of sine, it's just minus sine. And let's make this one red over here. And then color is equal to red. And then I run it. And in this case, as you're going to see, actually our derivative is not too good. It's going to be, our sine derivative is actually, our estimate of our finite differences one is actually way off. But as we start increasing the points, so if I do 80 points, It gets a little bit better. And now if I let's try 100 points. Oh, I forgot to define the delta. That's why it's off. I keep on forgetting that bit of code. That's actually why it's off. Let me come back to 20. It'll still be off, but delta is going to be x of 1 minus x of 0, right? I have to define the delta for the value I'm using, and now I run it, and you actually see them actually perfectly overlap with the two. If I come down to x of 10, right, it's going to be a little bit worse, right? So we start seeing a gap. If I try 5 points, obviously it's going to be even worse. But if I have kind of my 20 points, I get a pretty accurate solution. And then if I do 100 points, which is kind of the standard, it's kind of indistinguishable from the analytic solution. And so the nice thing about finite differences is it provides a simple way for calculating derivatives. And once we can calculate derivatives, we can start thinking about solving for boundary value problems. And I'm going to continue that in the next video. This is just kind of the overview of finite differences. If you have questions, please post in the comment section or put them on Compass and Piazza, and we'll do our best to answer them as soon as possible. All right, thank you.